I will use this picture a few times, and just basically what we want to do is to send a signal from this end to this end, right? Of course, first thing we need to know is the signal itself, because that's what we're going to do, right? We're going to send a square wave signal from this end to this end. So this lecture is about the nature of this signal, okay? And we start with the so-called trapezoidal waveform. That's our signal, okay? And it has amplitude, that's A, and then the high duration, which is here, is tau, and then T is a period of the signal from this end to this end, that's T, and then 1 over T is the fundamental frequency of that signal. N times the fundamental frequency is the nth harmonic, okay? And then tau over T is defined as the duty cycle, or the percentage of the time when the pulse is high, okay? So this tau over T is defined as a duty cycle, okay? So this is the signal. So this is the signal we want to transmit from the sender to receiver, okay? All right. Of course, this is a non-ideal signal where you have some ringing that will cause the so-called overshoot or undershoot. There's some transitions from high to low that may not be monotonic. For example, here you can see that the transition goes from high to low and then goes high again. That may cause problem, okay? And then there's also ringing. So this is basically the actual physical signal that once it's transmitted, it becomes distorted, okay? So to understand this signal, because this is a periodic signal, so we can use the Fourier series to understand what signal is about, right? Okay. So I'm going to go through this very quickly. This is a two-sided Fourier series expansion of the signal, okay? And then you get the coefficient for each term, and then the phase of each term, okay? So, and this is how you can calculate the coefficient by this integration, okay? And you can do a two-sided or one-sided representation of the signal, okay? This is an example of a square wave, okay, with 50% duty cycle. That is the high is half of the period, okay? So this signal can be represented by sinusoidal expansion or Fourier series expansion. You can see that this is the fundamental frequency, which is W of 0 is 2 pi times the fundamental frequency, and then this is the third harmonic, fifth harmonic. So this signal, this 50% duty cycle signal, only have non-zero components for odd harmonics, okay? Third harmonic, fifth harmonic, and seventh harmonic, and so on, okay? So this is a simplest square wave expansion, okay? All right, and of course, this is the illustration of how you can use sinusoidal signal to represent a square wave. Actually, we only used 1, 2, 3, four sinusoidal signals: fundamental frequency, and third harmonic, fifth harmonic, seventh harmonic, and we can represent a pretty good square wave. Okay. All right. For any arbitrary rectangular waveform with arbitrary duty cycle, we can represent that with a Fourier series. Okay, we can get a Fourier series expansion, and then find the coefficient of this Fourier series. Okay, and then the A sub 0 is a DC component. You notice that this is basically the average of the DC, average of this area, right? A is amplitude, tau is a pulse width, T is is a period. So it's A times tau is the area of this pulse. So you divide it by T, so you basically have a DC average. Okay, so this is DC, and then each of this is one harmonic of this signal. Okay, so if you do this expansion in complex domain, then you can get this coefficient. Okay, this is DC. Okay, and this is a double-ended, a two-sided expansion. N goes from negative infinity to infinity. Okay, and then C sub n, you can represent C sub n, the coefficient with this complex number, with this amplitude here and the phase there. Okay, so if you just take the amplitude of this C sub n, okay, then you can represent this coefficient with a DC component multiplied by this function. Okay, and this function is called a sinc function. On top of this, the numerator of this function is a sine function. The denominator of this function is just a single linear variable of this sine function. Okay, so this is so-called a sinc function. Okay, and of course they have angles as well. This is magnitude, this is angle. So that's this coefficient. And if you represent this rectangular waveform with a Fourier expansion of the signal. Okay, and this is the illustration of time domain signal and the frequency domain amplitudes. Okay, so in time domain we have a square wave with a duty cycle here, but in frequency domain you can see that this is a DC, and this is a fundamental frequency, amplitude, and then harmonics. Okay, so that's basically time domain and frequency domain representation of the signal. Okay, all right. But if you just look at just this envelope, okay, you can zoom in to this envelope. Okay, if you take this sinc function, you make it you represent this with log, with dB. dB is 20 log natural log. Okay, and then of this function. Okay, so if you say 20 log of this function, you can have two terms. First term is from the top, okay, numerator. The second term is from the denominator. Okay, and then you can represent this in both as Bode plot. Okay, and with this. Okay. And you have a break frequency here, and then you have a negative 20 dB per decade reduction there. Okay, that negative 20 dB is represented by this. Okay, and that gives you the negative 20 dB. Okay, and this term is always very small or negative. Okay, it's always very small. Okay, so basically you have more or less a constant amplitude, and then at some breakpoint, and then the breakpoint is defined as when x is equal to 1. Okay, when x is equal to 1, you have a breakpoint where, and after the breakpoint, this envelope of this sinc function decreases at negative 20 dB per decade. Okay, so that's how we can understand this sinc function. Okay, all right. Any question here about dB representation of this sinc function? This is just linear representation of this function, and this is the dB representation of the sinc function. Okay, if you represent the linear function, you can see this looks like this. Okay, if you represent it in dB, then you can study so-called envelope. Okay, and notice that this point is called the breakpoint frequency, where x is 1. Okay, x is 1 is called breakpoint. All right. Any question? Okay. So, and this is a general rectangular wave form Fourier series representation of this. This is the amplitude of the Fourier series. Okay. We can study the exact value of this function and then the bound value. Okay. Bound values are the values on this line. These are called bound values. Okay. The value on this line is called bound value. You can see that the exact value, some exact values are the same as the bound value, some are much lower than the bound value. Okay, so this bound is so-called upper bound. That basically means all the values here will be below this bound. Okay, so to show that it really is true, let's look at look at this function, which is 100 megahertz signal with 20% duty cycle, and then amplitude of 1. That's this signal, and this is its Fourier series expansion. Okay, if you look at the exact value, this top is the exact value at 100 megahertz, 200 megahertz. Those are harmonics of this signal, and then the bound value. You can see that the exact value is all below the bound value. For example, at 500 megahertz, the exact value is 0. The bound value is 102. Okay, so, and that's why we can call this a bound value. Okay, the way I obtain this bound value is I use a software package, and I'm going to assign a homework assignment this afternoon that you're going to use this for homework number 2. You're going to use this software package from University of Missouri to calculate the Fourier series amplitude of Fourier series expansion of this signal. Okay, I'm going to show you this a little bit later. Okay, all right. So this is about a rectangular waveform. That is the rise time of fall time 0. Okay, that's that signal. All right. What if we have a rise time of fall time? Okay, in this case, okay, we define the pulse width as high duration of a pulse. Okay, defined at the half of the amplitude, half point of the amplitude. Okay, from this point we define that's how this pulse width is defined. Okay, the rise time is defined as from 10% of the amplitude to 90% of amplitude. That's usually how it's defined. So from 10% here to 90% here is defined as the rise time of the signal. Again, the fall time is from 90% to 10%. This is basically the definition. In general, that's how these parameters are defined. Okay, so what if you have this signal? What is this Fourier series expansion? How do we get this Fourier series expansion? Okay, of course we can do it with general expression. Then we can do integration over one period and to find the coefficient, right? But that's not. It's a little bit hard to do because you have to do. If you go back to the Fourier series expansion, notice that you have to do this integration of that signal. Okay, of that trapezoidal signal, which is this signal here. Then you can find the coefficients. Okay, and there's another way to do that. By the way, I copied this from a book by Clinton Paul. It's called Introduction to Electromagnetic Compatibility. We used to use this as a textbook. Okay, and now we switched to another textbook. But this idea, the whole presentation is from Clinton Paul. Okay, all right. So how do we do this? How do we find the Fourier series expansion of this signal? Okay, the way to do that is to convert that signal to something else. Okay, so basically, let me draw this here. Let me show you just a little bit of the idea. Okay, so that you can focus on the idea. All right, so we just need one period, right? Okay, so, and this is TR, that's rise time, this is TF, fall time, okay, and you have a tau and A, okay. So, let's see this is a function, the function itself. So what we're going to do is we can take a derivative of this function, okay. If we take the derivative of this function, what do we get? What do we get? We take the derivative of this function. From 0 to TR, what is the value? The amplitude is A, right? and then rise time is t sub r. We have a constant, right? What is constant? A over t sub r. From t sub r to here, what do we have? 0, right? 0. And then from here to this point, what do we have? A negative value, right? A over t sub f. Okay, negative of that. And then we have 0 again. All right. So this is the first thing. And then we take the second derivative of this function. Now what do we get? We have so-called impulse function, right? The impulse function has 0 time and then an amplitude. It's an infinite pulse. Okay, so we're going to have an impulse function here, an impulse function here, an impulse function here, an impulse function here, right? Okay. Where is the eraser? Thank you. So this one goes down, this one goes up. Okay. And then the amplitude of this is still A t sub r. Okay. And then the amplitude of this is also A t sub r. Okay. And the only problem is the delay time. Okay. So of course the time, this is 0. Okay. This is tr. And over here it's negative A t sub f. Okay. The time is a little bit hard to describe. Okay. The time here is you can see this is tau here. Okay. And so this is half of t sub r, and this is half of t sub f, right? So the time instant, this time instant is t sub r over 2 plus tau and minus t sub f over 2. Is that right? So this is t sub r over 2 here. This is tau all the way here, and you need to subtract this part. Okay, so that's this time instant. That's the time instant here. Okay, and this time instant is tau plus t sub r over 2 plus t sub f over 2. Okay, so you have 4 time instances. This is t sub r, this is 0, that's this. Okay, why do we do this? Okay, because we want to use some properties of a Fourier transform. Okay, this is what I've done here. Wait, is that correct? Yeah. 1, 2, 3, 4. Okay. And this is the properties of a Fourier transform. Okay. One is called linearity, where if xt coefficient of xt is this and yt is that, okay, then if you add them together, you basically add them in a frequency domain. Okay. And the second is time shifting. Okay. If this xt has this Fourier series expansion coefficient, if you shift in time domain, you basically multiply a phase in frequency domain. Okay. And the second is this delta function, impulse function. If you integrate the impulse function, you get this amplitude. Okay. So, And third is this fourth is integration of cosine square, okay, from 0 to t. That will give you just basically t over 2. Okay. The fifth one is what we're going to use here. Okay. If this is Fourier series expansion, then its derivative will have Fourier series expansion multiplied by this phase factor. Okay. So using these properties, okay. For example, if we can get Fourier series expansion of this second derivative, I'm not sure my notation is correct, but if this is a Fourier series expansion of this second derivative, okay, then the Fourier series expansion of this original function, if you look at how, and that's is going to be this divided by j n omega 0 square, right? So in order to get Fourier series expansion of this signal, okay, and we will take the derivative of this signal, and then to get this impulse functions, then we can get this coefficient of this impulse function easily, because the integration is pretty simple, right? If you do integration, you just get this amplitude back, except for the delay. Okay, and then each of the delay is going to be just that factor there. Okay, see the time delay there. Time delay basically is to introduce a phase, okay, of this. All right. So once we obtain this, then we divide this by square of this, and then we can get the original coefficient. Okay. All right. Now it's just messy. Okay. There are a lot of details, but the principle is pretty simple. Okay. So there. Okay. So this is the Fourier series expansion of the second derivative. Okay. And notice that those are factors, these are delay factors. Notice that all these are delay factors. So once you obtain this, you divide this by the square of this, and then you can get Cn. Okay. All right. So there's a lot of details, but the principle is that it's pretty simple. Okay. So if you're careful, you should be able to do it. Okay. All right. So this is the coefficient of the Fourier series expansion for trapezoidal waveform. Okay. If we cannot make any assumption about rise time, fall time, okay, this is rise time, this is fall time, there's not much we can do. We just need to just stay here, just use this. Okay, this is all we can do. But if we make one more assumption, that is, the rise time is equal to fall time. Once we make this assumption, then we can simplify this expression to get this expression. Okay, where you have a DC component here, you have this sinc function, the first sinc function, and then second sinc function. Okay, the first sinc function is related to the duration, the pulse width, tau. This is pulse width. The second sinc function is related to the rise time. This is rise time. Okay. This is only true if you assume the rise time is equal to fall time. Otherwise, it's not true anymore. Okay. So, and that's how we can obtain Fourier series expansion coefficient for trapezoidal waveform.